Welcome everyone to the Center of Econometrics and Business Analytics seminar series. Today we are having Tassos Magdalinos from Southampton University. His talk is about uniform and distribution-free inference with general autoregressive processes. So Tassos, you have approximately 1 hour. And do you want the questions during the talk or at the end?
I really don't mind. Please,
okay.
I don't mind at all. So.
Okay, thank you.
Perfect. Well, thank you very much for inviting me. It's next time hopefully for live. I have never visited Russia before, and you're trying to do something, but then COVID hit. So it's hopefully next time. From live. So this is joint work with Katerina Petrova from Universitat Pompeu Fabra in Barcelona, and the aim is to so let's see how it goes. I'm trying to. Okay, great. So the aim is to get a uniform confidence interval for an AR1 process, or for more general sort of predictive regression models on both sides of Unity. So basically we Mikushev and others have done work on uniform confidence intervals for stationary and unit root processes, and we want to extend this. We will provide alternative but uniform confidence intervals for autoregressive processes that would be either stationary, unit root or local to Unity, or explosive and or the rest of the intermediate persistence counterparts. Okay, so we will do that by constructing basically establishing a new instrumental variable procedure, which is a little bit the same in flavor as has the same flavor as the instrument, the IVX instrument that we have established with Peter in 2009, but of course it will be different. It will be a different instrument that will be essentially tailor-made to get all of the autoregressive spectrum. So it will be the ideas are related to the paper with Peter, but both the instrument construction and the corresponding T statistics are different, and also of course the limit theory is new. So so we will get what we aim for in the end is to have no discontinuity, to use the instrumental variable procedure in order to get no discontinuities in the limit distribution of distribution. Of course, we'll have discontinuities for estimation, but the idea is that these discontinuities will be all within a mixed normal limit, within the family of mixed normal distributions, and therefore the limit distribution of the T statistic would be standard normal in all cases. So we will do that, with uniform size, and in passing, we will also establish a distribution-free procedure for the purely explosive case. This is actually a first, and provides a solution to a well-known problem posed by D.W. Anderson in his 1959 paper in the Annals of Mathematical Statistics. Basically, that the OLS or the OLS estimator has a standard Cauchy distribution if and only if it is actually a maximum likelihood estimator. Okay, so if so in the general OLS case, the distribution of the OLS estimator and also of the t-statistic is basically driven completely by the innovations of the autoregressive process. So just a little plan for the talk. I will give some motivation and a little bit of discussion of the different persistence regions that we have in autoregression, mainly in order to help understand the construction of the instrument. Then obviously I'll give some some limit theory and some simulations, and then one of the main reasons why we consider such an extension, apart from the pure econometric theory, sort of mathematical generalization, it is there are models of the dynamic evolution of epidemics, like the COVID-19 epidemic that we are facing at the moment, that basically when they are linearized, and put a stochastic component is introduced, like this SIR models, after linearization, basically they become like an autoregressive. The number of infections follows an autoregressive process, and it turns out that the autoregressive parameter, that the root of this first order autoregressive process has a one-to-one correspondence with the basic reproduction number of the epidemic, and one can show that it is that the basic reproduction number will be greater or equal than 1. So basically, you lose track of the epidemic if and only if the autoregressive parameter of the number of infections at time t is greater or equal than 1. So basically, by constructing a confidence interval for the autoregressive parameter over the whole autoregressive spectrum, including explosive processes, we are able to get some reliable confidence intervals on the basic reproduction number of any epidemic, including the COVID-19. Provided that we believe the linearized form of the SIR model. Okay, so let's go to the main part of the talk. Well, there's no point spending too much time on this in front of this audience. So we know we have a first order autoregression. We know that this has that the limit theory limit theory in first order autoregression has gives rise to very different limit distributions for the estimators and tests. So we all know what happens in the stationarity region. You get root inconsistency and the asymptotic normality. We all know what happens again in the local to unit root region. So basically, okay, perhaps it's worth spending a moment discussing a little bit why we are considering topological neighborhoods of unity. We do so in order to get uniform inference. Okay, so basically there are we need to get a confidence interval, a reliable confidence interval for the autoregressive parameter when you have sequence of drifting parameters rho n that converge to some rho, and then rho is anywhere in the -1 infinity region. Okay, so then of course immediately we get issues with uniformity, and the way to resolve this is to first consider these different categorizations, so to speak, of autoregressive behavior, and then trying to put them together in one sort of uniform procedure. So in stationarity, of course, we have this standard limit behavior. Now, in the local to unit root case, we have Peter's seminal paper in Biometrica and Jarnway's paper in the Annals of Statistics that tell us how autoregression works. And in the explosive region, this is something that people might have forgotten, so I'd like to spend a couple of minutes here. So in the explosive region, we go back to the asymptotics were first derived in the IID normal case by John White, and a paper in 1958 paper in the Annals of Mathematical Statistics, and then Anderson followed suit 1 year later in the same journal and highlighted the problem that we are going to talk about now, which is that essentially the normalized and standardized, the centered and standardized OLS estimator converges in distribution to a ratio of random variables. Well, only in the IID case, or in the you could get martingale difference here, but the main issue is that both the distribution of the denominator here and the numerator here are driven by the innovations UT of the autoregressive process. So what we have in mind is an autoregressive process. XT is raw XT minus 1 plus UT, and what Anderson highlighted by using martingale theory is that the limit distribution here, both of the denominator and in the numerator, basically are driven entirely by the innovation process by the innovations UT of the autoregressive process. And this is so because this limit here, I beg your pardon, this limit here converges almost surely. Okay, so there is no asymptotic negligibility for a central limit theorem. This thing converges by the martingale convergence theorem, and therefore you change something in the U, and the distribution of Z changes, and also the distribution of Y changes. Okay, so by simple inspection of Z, of course, when the U's are normal, then since linear combination of normal random variables are normal, then this will become normal, and the ratio will become Cauchy. Okay, which was the original result by White. So if we have a look at these sums here, it's clear that the first few elements of the sum contribute here, and the last few elements of the sum contribute here. So just to give and the same of course happens if you have a predictive regression here. So beta here is you have YT is mu plus beta YT minus XT minus 1 plus epsilon t, and then XT is a standard sort of AR1 process. So then if the AR1 process is explosive, you get exactly the same thing in a predictive regression setup here. Okay, so just to give an illustration of what happens in the explosive case, let's have a look at we're having a look at the predictive regression setup here with Rustam and others have worked on this. So you have a predictive regression. YT is yt on xt minus 1, and then xt minus 1 is an explosive process. Okay, it's an explosive process with autoregressive parameter 1.09. So what we do is first you have the U's being coming from the U's here are the this is the error of the autoregression, and this is the error of the model of the predictive regression. So consider them first independent standard normal, and run a t-statistic for the null beta is equal to 0, and you get the fine size here, okay, for 20, 50, 100, and 500 observations. So what we do in the second column is we change the last observation of epsilon. Okay, so instead of having a unit variance, it has variance equal to 2 and variance equal to 3. So in a normal sort of in a general asymptotic theory framework where you would have a central limit theorem, you would have asymptotic negligibility. So just changing one epsilon in a large sample would not make a difference. Okay, but you see here that the size deteriorates immediately, and more importantly, as you increase the sample size, the size deteriorates. So basically, what this suggests is that this the lack of limit, the lack of central limit, general inference here for beta matters. Okay, you just distort slightly the variance of the last observation, and the size deteriorates rapidly and does not improve with the sample size. Okay, so what remains to talk about in that motivation is just the intermediate regions here, the sort of near stationary and near or mildly explosive region. And the main reason why we talk about this is that we construct our instruments like this. So in the near stationary region, Peter and I have written a paper in the Journal of Econometrics on both sort of basically completing the limit theory here. So the near stationary region is a neighborhood of a unit root where kn here increases to infinity slower than n. Okay, so it's basically a neighborhood of unity with radius larger than the local to unity region. And what we have done is we showed for Peter and I showed that in the near stationary case we essentially get ergodic asymptotics, but with different rate of convergence. So with the rate of convergence, the square root of n times kn, where kn is the radial parameter here, but you still get a law of large numbers and the central limit theorem. And in the mildly explosive case, which is exactly the same process, but on the right of unity here, you get asymptotic behavior that looks like an explosive asymptotic behavior. However, the key difference is that in this ratio here, yn and zn, these sums here without the normalization kn, these sums diverge. So they need to be so no martingale convergence theory applies, and actually because of divergence of these sums, you have to divide it by something. That something depends again on the radial parameter, and central limit theory applies instead of martingale convergence theory, which is a great thing because we get general asymptotic inference for the OLS estimator. This helps us because we will try to get general asymptotic inference in this explosive region here by setting up a mildly explosive instrument for this side and setting a near stationary instrument for this side. Okay, so finally the last thing in the of existing work is to talk about quickly is our work with Peter in 2009, and subsequently a review of financial studies paper with Alex Kostakis and Michalis Stamatogiannis. So this gives we set up an instrument. We managed to unify inference in this region here by using a so-called what Peter called an IVX instrument. So what we do is we employ delta xt as a residual, as a quasi-residual, and then construct something that is that resembles a near stationary process. Basically, we set up an AR1 process based on the differences of the x's using a chosen artificial autoregressive route. Okay, so this is 1 minus 1 over kn, where kn is designed to place the process in this region here. Okay, so kn goes to infinity, so we are in a neighborhood of a unit root, but this neighborhood is larger than the standard sort of local to unity type of neighborhoods. And the IVX estimators here are simply basically an estimator, an IV estimator, where you use Z. This is just a standard IV estimator that employs Z instead of thus constructed instead of X. Okay, and the same in the so this rho is for autoregression. This beta hat again is for predictive regression, and what we did show in this paper with Peter is that in all the sort of green region, in all the region that we are from local to unity up to the stationary region, we get asymptotic mixed normality. Of course, in the local to unity region, we would get a random variance that depends on Ornstein-Uhlebeck stuff. And the resulting statistics crucially would be asymptotically normal. Okay, so the first contribution of this paper is we do something similar on this region of on the right region of unity. Okay, we basically set up an instrument that is in Inspirit similar to an IVX instrument, but has two important differences. First, it's mildly explosive, so rho and z in the instrumentation is chosen to bring the process in this sort of region. Okay, which is of course very intuitive, because you would like the instrument to sort of follow the original regressor. So if we have explosive stuff, we would like to follow it with something that is kind of explosive. What multi-explosivity buys us is that, of course, is general central limit theory. Okay, so basically, even if you have we will show that even if you have an explosive process, if you instrument it by a mildly explosive process, the resulting estimator would be distribution free. Okay, so this would solve the first problem highlighted by Anderson. Okay, the second difference is that instead of constructing the quasi innovations of our instrument by differencing the x's, Of course, this would be unacceptable for an explosive process, because it's like it's like differentiating an exponential, right? So you can difference an explosive process 1,000,000 times, it will remain an explosive process. So what we do is, instead of the delta x's, we use the OLS residuals of the OLS residuals. So what we do is what we show is that in this case, so the first contribution is that we show that we get asymptotic mixed normality in all these highlighted regions. So basically, we get asymptotic mixed normality for anything that is as persistent as a local to unity process and to the right. Okay, and now of course we have two instruments. We have the IVX instrument with Peter, which works on this side, including the local to unity. We have this new instrument with Katerina that works again on that green area, and of course the issue is to combine it, right? In order to combine it, we would need let me see if in order to combine it and bring do everything in one go with the same instrument, we need a little bit of information on where we are. But what saves the day is that both instruments work in the local to unity in the local to unity region. So basically, we don't really want the sign of C, right? If you parameterize your autoregressive, well, let me show it here. So if you have if your autoregressive root is 1 plus C over Kn, what you would like is, of course, information on the sign of C. So you say that if C is negative, I use the original instrument. If C is positive, I use the new instrument. Of course, this is infeasible. However, if you look at it more carefully, you don't really need the information of the sign of C. Since both instruments work in here, what you need is you want to, if you parameterize rho as 1 plus C over n, what you need to know is if C is plus, you need to differentiate C being minus infinity from C being plus infinity. Okay, and for this you have enough information in OLS. So I remind you that so if Kn here is the true persistence of the autoregression. So if what I'm saying is that I don't care what C is here, but if we are either in the mildly explosive and explosive region or the near stationary and stationary region, then we can use this quantity here as an indicator of which instrument to use, because basically this quantity would converge in probability to minus infinity if we are in the near stationary or stationary region, and to plus infinity if we are in the mildly explosive or explosive region. Okay, and of course it's going to converge to a real number. Well, no, sorry, it's going to converge to a real random variable. This Kc here depends on functions of the Ornstein-Uhlenbeck process in the local to unity region, so it will be non-informative. But we don't really care about that, because both instruments we show that both instruments work in the local to unity case. So basically this is how we construct the new instrument. So we take we define based on the previous discussion here, we use this quantity as an indicator of which instrument to use. So this sequence of events here, Fn, is designed to do this thing. So you take Fn is something that would send you into the near stationary region, and its complement would send you to the mildly explosive region, and then you have a combined instrument Z, where you choose the autoregressive the autoregressive root of the instrument like this. So you have phi1n is a near stationary root, and phi2n is a near explosive root, is a mildly explosive root here. And you have, and of course, you indicate, right? So you have indicator this plus indicator that, and utilder is the innovations of the instruments here are the IVX innovations that we have with Peter if you choose a near stationary instruments, and as we indicated before, the OLS residuals if we are in the sort of near explosive instrument. So the idea is that in the stationary and near stationary regions, these indicator functions here would converge in probability to 1, and they would converge in probability to 0 in the mild explosive and explosive region. And in the local to unity region, there would be a combination of the two instruments. So basically so in the near stationary, for data generating processes here, in the stationary and near stationary region, we will recover the IVX instrument that we had with Peter. In this region, we will recover the near explosive instrument that we talked about a couple of slides before, and in this local to unity region, we will get a random linear combination of the two instruments, which crucially we will show that preserves asymptotic mixed normality. Okay, asymptotic mixed Gaussian. So here's the model. So this is pretty standard. We have the only thing that we impose a conditional homoscedasticity, but we can.
Hi, Tassos.
Yes.
Hi. So maybe before we go into details about the assumptions, for me, it's still a little bit like a magic box, this IVX instrument. So can you maybe a little bit more on the intuitive side, like why on one side you use this instrument and you obtain mixed normality, and then this new set of instruments on the other side? So because usually, like in microeconometrics, we know something how instrument works, so they kind of orthogonalize to the errors or to the genius part of the data. And so on more intuitive level, like how to see this, and then maybe we can jump into combinations.
Yeah. So the assumptions are not very. We've done most of the work. Okay. So let's. So what you know about in microeconometrics, you know something about another process, right? So you use it in order to to fix the problems that you may have either with identification or with whatever you have. So here you have a process that xt. So the way that we correct it is basically we're using this process xt in order to generate an instrument of which we control the persistence. We control the integration order. Okay. So we know that. So we know in near stationary region here, if your true process X is in the near stationary region here, then you have a law of large numbers and a central limit theorem with non-standard rates of convergence, but basically you have very nice limit theory. Okay, so what you do in the IVX in the original paper is that you take a process that may or may not be a unit root. Okay, you difference it. So if it is a unit root process or a local to unity, this would be delta xt here would be simple residuals. Okay, so it would be the UTs, or in the local to unity case, there would be UTs with some error of order 1/n. Okay, so then you use these as your innovations. Okay, of course they're not innovations; they're innovations plus noise, and then you accumulate. You construct a new time series with this rate. This rate is explicitly controlled to bring you here. Okay. So because this kn here is chosen to diverge, but at rates strictly less than 1/n. Okay, you choose this thing. How you choose it is a different story, but let's just agree that you choose it. Okay, so now if you the intuition is that if you have a unit root process, then what happens is that if you have a true unit root process, this would be a true near stationary process. Okay, and then once you do the IV estimation here, basically the nice properties of near stationary process would give you asymptotic normality in the numerator. Okay, because of what we have here. Okay, ZT is a process here, so it would give you asymptotic normality. Okay, and while at the same time in the denominator you would get something random, right? Because still xt is a non-ergodic process, but one of the key things is to show that this random variance would be independent of the numerator. So basically, you would be in a mixed Gaussian framework. Now, what happens if you are so this is the sort of prototypical idea, right? What happens if xt is not a unit root process? If it's a local to unity process, more or less the same things will happen. You will just have a different variance. And if xt happens to be a near stationary or stationary process, then what would happen is that you would get near stationary asymptotics if your original near stationary process is more persistent than ZT, than your instrument. If your instrument, if your true process X is in here, you may well choose an instrument that is here. Okay, so basically you may well choose a more persistent instrument. In this case, the IV procedure collapses to LS. Okay, this would always happen, for example, if you're stationary. If your XT is a stationary process and you use IVX, you would get your instrument would be here. Okay, and then basically the asymptotics for the IVX estimate would just collapse to the OLS estimator, which is great because for stationary and near stationary regressors, you have standard limit theory. Okay, now we're trying to do the same with the on that side of unity with a mildly explosive instrument. The reason why we use the U hats here instead of the OLS residuals instead of the differences is because we want to deal with this explosive region here in a way that gets in the way that we have central limit theory. Okay, so that our IV estimator does not, the limit theory for IV estimator does not depend on the errors of the autoregressive process. So that's so now once you have this idea, then the issue is how to switch it. Okay, so you have these two instruments. The idea is how to switch it, and the key thing is that both instruments work here. So you don't need information in the local to unity region. You don't need information, you don't need this information. You can plug in a linear combination of these instruments, and we show in the paper that what you get out is asymptotic mixed Gaussianity for the IV estimator and asymptotic mixed normality for the corresponding t statistic. Sorry, asymptotic standard normality, standard Gaussianity for the t statistic. Okay, so then you but what we need information is you know, what I really don't want is to use a mildly explosive instrument for a stationary regressor and a near stationary regressor for an explosive instrument. Okay, and I can do this because I get information on basically whether. Oops. I can get information on where I am, essentially from these heuristics. Okay, because if I need to differentiate this quantity here would tend to minus infinity if I have a near stationary or stationary regressor, and to plus infinity if I have a mildly explosive or explosive regressor. So I can use this information here to construct my instrument. And in fact, I can show is that this indicator function converges to 1 in the stationary near stationary region and to 0 at mildly explosive and explosive region arbitrarily fast, because this is essentially a sign restriction, right? So if this thing becomes minus infinity, at some point it will it will become 0 for all but finitely many n, and it will become here, and it will become 1 for all but finitely many n here. I don't know if I've covered you. I'm sorry. I may have over explained.
I appreciate it. Thank you very much, Tassos.
But did this make sense? So
yes.
So basically, in the simplest case, you shave. Say you have a unit root and you use the original instrument. You shave some of the persistence, some of the rate of convergence of the original series, and you construct an instrument like that. You see, this is what you input. This is what you use the time series properties to construct a new process that whose integration order you govern.
And also, what happens if you use the wrong instrument? So if you use explosive instruments on the stationary region and other way around.
Yeah,
so here you pick the right instrument. If you just blindly use IVX to the right, or
so for the so if you use a mildly explosive instrument in the stationary region, you will get inconsistency. Okay, you would get inconsistency of the resulting IV estimator. If you which is obviously very bad, but of course, with this procedure we show that it does not happen, right? This is a sort of data-driven procedure that tells you what happens, basically gives you the correct result. If you use the near stationary instrument here, the situation is not so bad. So there's a paper by Phillips and Lee in the Journal of Econometrics 2016 that basically tells you that you would you would recover the OLS estimator here. You would get essentially mixed you would get mildly explosive. You would get mildly explosive asymptotics in the mildly explosive region and explosive asymptotics in the explosive region. The problem, of course, with this is that the OLS estimator here is problematic because it depends on the distribution of the innovations. So you would not get. I mean, you can do various things, right? You can bootstrap, you can do whatever you want, but consistency of the bootstrap would bring you to OLS, and the OLS here is problematic. The OLS depends on, if you have Gaussian, if you have Gaussian innovations, you're fine. If you have non-Gaussian innovations, or you have or something changes a little bit in the variance, you're in trouble. So that's what happens in a nutshell. So using an explosive instrument, the stationary region is catastrophic.
Catastrophic is inconsistent, but it has a limit. It doesn't diverge.
Well, it's inconsistent. I mean, once you have inconsistency, there's no point looking for limit distributions, right? At least in my mind.
Okay.
Yeah, so it's what you're doing doesn't make sense. If you use the near stationary instrument, the explosive case, it makes sense, but you're stuck with the problem of Anderson, with the problem of lack of general asymptotic theory. Okay.
Excellent. Thank you very much, Tassos.
Rustam, did you want to ask something? Okay, sorry. No.
I was going to discuss some robust inference approaches using mixed normality, perhaps beta at the end.
Okay. Yeah. Do you want to discuss it now or leave it for later?
Maybe after the talk.
Okay. Okay. So then, okay, let's run through. Okay, you have 10 minutes. So fine. So sort of usual type of setup. So these are really two different statistical models. So the first aim is to take this as our statistical model and do uniform inference on rho under this assumption that rho n converges to rho somewhere in the anywhere between -1 and infinity. And the other one, of course, is that I have a different statistical problem. I have a predictive regression model. I want to do inference on beta, and xt is given by the second line. Okay. My assumptions are pretty standard. We can relax conditional homoscedasticity. The errors here for the first model would definitely have to be martingale differences if I'm interested in doing inference in rho. If I'm interested in doing inference on beta, of course, this use could be stationary linear processes, whatever. I impose conditional homoscedasticity. This is not this can be generalized, but you need to work more. And in addition, yes, we have a more or less standard assumption on the initial condition for x, and for the only thing that is not entirely standard is that for the purely explosive case, so when rho n converges to some number greater than 1, we need this condition here. This condition here, the likes of Rustam and Artem would recognize as one of the two sort of I cannot even pronounce it probably, Markizievich-Zygmunt conditions for generalized Markizievich-Zygmunt conditions. They appear on the book of Stout and Lai and Y. use them. Basically, what you need this for. The second one is covered by conditional homoscedasticity, so you don't need the second assumption. What you need this for is when you have what you need this for is when you have use being martingale differences here instead of when you have use being martingale differences here, you want this z infinity in the denominator to be non-zero almost surely, right? So this is what this gives you. Okay, this is in a paper by Lai and Y in the 80s. So let's show our results. Okay, so the
May I ask a quick question about martingale homoscedasticity assumption? I understand that it's standard, and also there are wide classes of martingales for which it's satisfied, like martingale transforms. Concerning extensions, where exactly it's used in martingale CLT, I suppose, right?
Yeah. So conditional homoscedasticity would be more, so in the numerator, right? So some, when you have some xt minus 1 times ut, right? It's much easier to do it when you have a conditional homoscedasticity. It can be done when you don't have conditional homoscedasticity, but you have to work more. You have to impose some sort of mixing condition and something like that. So
how about Garch time processes?
Yeah. In fact, I just got accepted the paper in econometric theory, doing this for a stationary Garch process.
And for those, is it satisfied?
No.
Of course not. Yeah.
No. So assume a Weygart processes, and I'm saying here that it can be done. I've done it for Garch for a parametric sort of Garch PQ process for a multivariate system. So you would have this being a vector and the beta here being a matrix. And having a multivariate Garch process for epsilon t, and a conditional homoscedastic process without parametric specification for ut. You can Kasparis and Wang did the multivariate, the univariate case. And in the univariate case, you can do things. You can do things without by imposing mixing conditions much easier than the multivariate case. So it's not. I assume all this away, but everything can be done for with conditional. With conditional heteroscedasticity. The only thing is that when x is strictly stationary, so when x is stationary, purely stationary, then you would have, so for the t statistic for your IVX or IV or whatever t statistic you do, you need a White correction. You would need to have a White type of correction for the variance, right? That I don't have here. But if you plug it in, then everything goes through, and then it becomes a problem of regularity conditions. Get the right strong mixing condition and stuff like that. And you need 4 moments. So here I only and you would need 4 moments. So here for the u's and the epsilons, I just say that it is a uniformly that the squares of these and the squares of these are uniformly integrable. So I only essentially impose a little bit more than second moments. Okay. Okay, fine. Sorry, I have 3 minutes. So let me. Okay. This is a slightly So So our testing theory would our robust sort of confidence intervals would only use this assumption. Of course, in order to get the limit distribution theory for estimation, you need something more more restrictive. You basically need to categorize autoregression, pretty much like the little graph that we have before. The neatest way to do this is this assumption 1 star that I have here, basically to say that the limit of n rho n minus 1 exists in the extended real line. So basically, this gives you categorization, right? So if this C here is a real number, you're in the local to unity region. If C is minus infinity, you are the near stationary and near stationary processes. And if C is plus infinity, you are in you have a near explosive or an explosive process. It's worth noting that this categorization is stronger than our assumption here. Because of course, you may get sequences like this sequence here that satisfy that converges to 1. They satisfy assumption 1, but of course they don't satisfy assumption 1 star. Okay, and the way we're going to do the asymptotics is I'm going to use assumption 1 star in order to get out the limit theory for the estimator. But then when a student dies, I will use a subsequence method to show that the statistic would be asymptotically standard normal under the more general under this more general condition here. Basically, what I can say is that assume that this holds, then you take any subsequence, then you have the sort of monotone subsequence lemma, right? So you can extract a monotone subsequence of this guy, and then you use your limit theory of estimation, and then you sort of recover you recover the because the t statistic would always be asymptotically standard normal. Then you have a standard sort of subsequence argument that shows you that the whole sequence of the t statistic is under corresponding confidence intervals will work under the more general assumption. So fine. So this is we've more or less dealt with all this. These are just the results. So given this categorization in assumption 1 star, I give results on limit theory of estimation. So our tilde here is my IVX. Oh, sorry, my new IV estimator, the combination of the near stationary and the near. Yes, so it is this and the near explosive instrument here. So this is the new estimator that we propose. Of course, under stationarity and near stationarity, you would get a standard normal distribution with the estimator as before, reducing to the OLS limit distribution if you happen to instrument with something more persistent here. For the explosive and mildly explosive case, so these are the results. So again, you have again, this is the same estimator, with slightly more complicated rates of convergence. What you get is a ratio of two random variables, as you would get in the explosive and mildly explosive case. But crucially, this continues to be mixed normal both in the mildly explosive case and in the purely explosive case. So in the mildly explosive case here, when x in the mildly explosive case here, when your rho n converges to 1 from above, then X would be a normal random variable. Y will always be a normal random variable here. So the ratio would be a Cauchy. When rho n converges to some positive rho, then this is no longer a Cauchy distribution. However, what we can, we get a ratio of a normal random variable and an independent random variable X, which has this form and is non-zero most surely because of this Markizievich-Zygmunt assumption that we have imposed. Okay, so in both cases you get asymptotic mixed normality. Crucially, the explosive rate rho to the n is preserved, and by using the instrument you can only you only lose that rate compared to the OLS estimator, which is at most, so Kn is Kn is at most it's strictly less than, dominated by root n, K2n the same. So basically this square root could be at most square root of n. Okay, in fact it would be something strictly dominated by the square root of n in the worst case scenario. So so still we have exponential rate of convergence, and crucially the asymptotic mixed Gaussianity in the explosive case here holds without any distributional assumptions on the U's. Now and finally, the final part of the estimation is that when you are in the local to unit root case, then what you have is your rate of convergence is a random combination of the two. Remember that this Fn here and its complement are sequence of sets, sequence of events rather, and you get again a mixed normal distribution. But of course, here you have in the variance you have functionals of Ornstein-Uhlenbeck process as you would expect to have, and same for the predictive regression setup. And then of course this is the main this is the main slide of the talk. So if you studentize, so this is the new estimator that we propose. If you now studentize based on this estimator, then what you get is and you use the confidence intervals again based on this studentized thing. What you get is that under the assumption that rho n converges to rho anywhere in the open -1 infinity interval, then the t-statistic would always be asymptotically standard normal, and the confidence interval associated with this t-statistic would have the right coverage rate, and this would be uniform. Okay, same for the predictive regression, setup, and that's that really. Uniform size is we combine results by Andrews, J, and Guggenberger and the sort of subsequential arguments. And we have some Monte Carlo, but I think I've run out of time. So we have some Monte Carlo simulations comparing our procedure here in the predictive regression setup with the procedure of Elliott, Muller, and Watson in Econometrics 2015, and then we have some size and power stuff. I don't know how much. Shall I stop here? And do I have 5 minutes?
Yes.
Okay, so these are some. Let's see something interesting. So okay, so the interesting thing is the standard. The interesting thing is the standard thing that they use in finance here. So So we are in this framework, and the correlate. So you have a correlation of the epsilon, and the correlation of the UT is large and negative. Okay, so minus 0.9 is the correlation between UT and epsilon t. And what we have here is okay. So we are green, and Elliott, Muller, and Watson are blue. And what we have here is size. So this is 5% the nominal size, and with 500 and 1,000. So what we see here is of course, Elliott, Muller, and Watson work up to here. Okay, they work up to rho is equal to 1. So what happens is that our size is fine here almost everywhere, apart from the unit root where it picks up. It becomes it becomes 10%. Of course, this drops as we increase the sample size, so it becomes close to the reason why the size is a little bit bites a little bit in the unit root here is because it's one-sided. So our two-sided test is actually very, very well sized, but the one-sided test seems to have a little bit of oversizing here, 8% instead of 5%. But this is only when you are very, very close to unity, right? So you have rho is equal to 1 here, and rho is 1 minus 25 over n, where n is equal to 1,000. So here you're very, very close to unity. So what happens is that we have on the one-sided test, these are our worst results. So our size picks up a little bit around unity, but otherwise is fine over the whole of the autoregression region. And for power, let's look at the same thing for power. And for power, we are green, and Elliott, Muller, and Watson are blue. For power, we are better than the Elliott, Muller, and Watson paper, again, with the exception of things that are very, very close to unity. Okay, so here we're a little bit unfair towards us, because we have because here we have 8% size instead of what do Elliott, Muller, and Watson have. Yeah, so they're perfectly sized here, but then their size collapses to 0, right? So basically what happens is that the short story is that we are, and these are the worst results for us. So we do better in terms of power everywhere apart from the unit root, and then the Elliott, Muller, and Watson procedure collapses on the right side of unity, whereas ours remains the same. Okay, so I should really stop here. We have a nice empirical application in terms of COVID-19 data, but there's no time. So it's I think it's a good time to I've run 10 minutes more. So what we do basically is we once you linearize this discretized susceptible, infected, recovered model, what you get is some sort of there is a standard linearization approach around the disease-free, so-called disease-free equilibrium. You linearize using the Jacobian matrix of the disease-free equilibrium, and then basically what you end up getting is a linear vector difference equation. So if you add some random error here, you turn it into a VAR1 process. Okay, but it's a very specific VAR1 process because the coefficients here in the Jacobian these are epidemiological coefficients, and they are linked theoretically together. So we can basically, once you add sort of a random error to this to this VAR, you end up with this model that you can put to the data. Okay, so this is I are the infections at time t, and R are the recovered or dead individuals at time t. So basically, what this tells you is that you have an autoregressive process for the number of infections, okay, with this autoregressive, with the red autoregressive root, and then this feeds into to the number of recovered individuals, right? You have a 0 here, so then you have a delta RT is equal to gamma times the number of infections plus error, and what you can show is that this autoregressive the autoregressive parameter of the number of infections here, the red number, is related to the basic reproduction number of the epidemic R0 through this formula, okay, and R0, the basic reproduction number of the epidemic, would be greater than 1 if and only if this autoregressive parameter is greater than 1, equal to 1 if and only if it's equal to 1, less than 1 if only if it's less than 1. So basically, what we do is we can use the robust confidence intervals for autoregression that we did and applied to by being careful to studentize the t-statistic for R0 for the basic reproduction number in a way that in the way that one should studentize. Then we use our robust confidence intervals in order to establish a robust confidence interval for the basic reproduction number. Okay, so I have taken too much of your time already, so I think I should stop here. So if you have questions or comments.
So in the empirical application, IT is the number of daily infections or cumulative?
No, I think it is the number of it is the number of infections at time t.
Up to time t or day t?
No. Sure. Up to time t. Yeah.
And what are your estimate? Do you have the estimates of the autoregressive parameter for that? The one on the next slide.
Not. I don't have the estimates. I have the actual confidence intervals. So I mean, obviously, I have the estimates, and Katerina will have the estimates too. So yeah, I mean, I'm not the best person to talk about the empirical application, but unfortunately, I only have the confidence intervals here for different countries.
We looked with Anton and co-authors on daily time series associated with the pandemic, including infections, and it looks like even daily ones are very persistent.
Even daily ones,
Even daily ones, and then we thought about predictive regressions involving those.
Yeah. Let me see. To be entirely honest with you, I am not entirely sure if IT is cumulative or at time t. I have to say. It shows how much of the empirical application I have done, but yeah.
Let us send you that paper. It would be
Yeah,
great if, to discuss, also to have your comments.
And of course, you know, obviously, in order to do this that type of empirical application, you know, perfectly, you would need to have a time varying coefficient, right? So the obvious restriction here is that you know, we say, okay, give me a stretch of time, enough data points, and I give you the right confidence intervals, irrespective of whether you know, the epidemic is in remission or it's exploding. Of course, you know, if one could do a time varying extension of that where you allow to switch as well, that would be great. But you know, we don't do that. Yeah. Well, and one more thing that I would say that it's empirically relevant here is that a lot of, so in economics, sometimes explosive processes are dealt a little bit in a condescending way. I say, okay, you do the math, but you know, we don't really explore, we don't really you know, observe explosive processes in economics. And of course, many people like Peter would disagree with that, but it is some sort of somehow common wisdom. But here, of course, at least half of the time in the COVID-19 epidemic, the number of infection was explosive, right? So it is entirely empirical relevant to look at this. And of course, if you really are explosive, you have like a 1.2 autoregressive parameter, then you use you know, OLS based intervals, then you'd better, you know, your innovations would better be Gaussian, because you know, if you want to say, because you have no limit, you have no central limit theory, no large sample, no general large sample theory. So it could be that you could say that, you know, the probability, which is of course fine for predictions, but if you want to say something like, you know, the basic reproduction number, you know, this week is between, you know, 1.1 and 1.2, then, you know, you could have the wrong coverage rate for this, if you have the wrong distribution on the innovations.
Please, colleagues, if there are any questions, comments. We've also working, Tassos, and wanted to ask, possibly discuss possible applications of robust inference methods using statistics applied to group estimates. We looked into applications using Cauchy estimators. Those converge to normals.
A paper with Muller, right? You had a paper.
Yeah, it's based on the statistic approach with Ulrich. We worked on applications to predictive regressions using instrumental variable estimation employed for groups of time series considered.
Yeah.
And maybe in the case of mixed normality, that would also work.
Yeah. I mean, you know, you know, the main reason why we took the Muller and Elliott paper, the Elliott, Muller and Watson paper, is because it is kind of considered to be the state of the art in sort of univariate predictive regression,